The end of Chapter 7 in our TRO textbook talks about quantum numbers. In old physics, often called classical physics or Newtonian physics, particles were just particles, and so you could describe position of a particle in 3 dimensions by looking at where it is on the x-axis side to side, where it is on the y-axis up and down, and where it is on the z-axis in the foreground and the background. So 3 coordinate positions describes 3-dimensional position. In the new physics, quantum mechanics, you can't know the exact position. So we have to describe where these things are, like electrons in an atom, using what are called quantum numbers. So we're going to describe position of electron in atom using quantum numbers. And so the quantum numbers that we're going to use are the lowercase n, lowercase l. I often make my l's a little cursive so you can tell the difference between my l's and my 1's. A lowercase m with a subscript l, m sub l. And then there's one more that, because electrons have this special property called spin, it's m with a subscript s, m sub s. So these quantum numbers are going to describe electrons in an atom because that will take into account that they're both particles and waves. So let's talk about each quantum number. The first is what we call the principal quantum number, n. The possible values of n, they always start at 1 and then go up by integer amounts, 1, 2, 3, and then it just keeps on going up infinitely. So 1 is the minimum value, and then it just keeps on going up from there. It can't be between 1 and 2, so it can't be 1.2 or 2.9. It's got to be these whole numbers. So what does this tell us? In your book, it says that the principal quantum number determines the energy of the electron. And it says it determines the size of the orbitals. The electrons are contained within orbitals. So if they're in different sized orbitals, they have different energy. So I want to be a little more specific than that, kind of talking about how size and energy are related. So imagine that we have the positive proton here, and then we have an orbital that's spherical in shape, so the electron's somewhere in there. And then instead, we look at another orbital that's much bigger. So if we look at these two, this would be bigger orbital. The electron could be close, or it could be way out there. In the smaller orbital, it could be close, or it could be close. So on average, a small orbital, the electron is closer to the positive proton. And negative electrons are attracted to positive protons, so that's a good thing. And another way to say good in science is that it is low energy. So if you have a smaller orbital, it's going to be closer, the electron is, and that's going to be lower in energy. And that's why they talk about energy and size being the 2 factors to look at. The n value is also called the shell. So for example, n equals 1 is often referred to as the first shell, or the first level. And sometimes this first level, since it's closest, is called the ground level or the ground shell, because like the first floor of a building is often called the ground floor. Now we'll move on to the next quantum number. And this one is again, a lowercase l, and it's called the angular momentum quantum number. The possible values here depend on the shell. They depend on your n value. So L always starts at 0. That's always the lowest. It goes up by whole numbers, 1, 2, etc. And the maximum is n minus 1. So the minimum is always 0. The maximum is always n minus 1. So if we were to look at a couple of examples, let's say we say if n is 1, then L always starts at 0. The maximum value, n minus 1, is going to be 1 minus 1, which is 0. So it goes from 0 to 0, so essentially there's only one possible value, 0. Similarly, if instead, let's say we said if n is equal to 3, then L can be 0. That's where we always start. The maximum is n minus 1, so 3 minus 1 is 2. That's the maximum. And what's in between 0 and 2? L equals 1. So in n equals 1 shell, in the first shell, there is one value of L, one subshell. So n is the shell, L is the subshell. In the third shell, there are 1, 2, 3 values. There are 3 subshells. We could also look at what this tells us. And in your textbook, it says that the value of L determines the shape of the orbitals. So if L equals 0, it turns out that the shape of the orbitals are spherical. If L equals 1, in that subshell, the shapes are dumbbell shapes. So spherical shapes, which means, essentially round but three-dimensional. Dumbbell shapes, where you have a lobe on one side and a lobe on the other side. So in the L equals 0 subshell, the electrons are somewhere around the nucleus in the middle. In an L equals 1 subshell, they're either on the left side or on the right side, and more accurately, they're on both sides at the same time. Now, each subshell has its unique name. Each subshell has a one-letter name. So, for example, if we look at each subshell starting at 0, 1, 2, 3, 4, the L equals 0 is called an S subshell. L equals 1 is called a P subshell. L equals 2 is a D. 3 is F. After this, it starts going in alphabetical order. What comes after F in the alphabet is G, then it goes H, and keeps going I, J, K, etc. So unfortunately, you just kind of have to memorize these first few letters. Later on, it's easier because it's alphabetical. There is some history behind these. It turns out that when light makes electrons transition between the third subshell, the lines of light are very skinny, very thin. Another word for that is fine. So it gives fine lines. That's where the name for F came from. When light makes electrons transition in here, it gives very blurry lines. Another word for blurry is diffuse. You don't need to know these historical reasons, but there are some. Unfortunately, you just kind of have to memorize these. each subshell has different shapes. The shapes that we focus on are the sphere of the S and the dumbbell shape of the P. You can see some of the other shapes in your textbook. Instead of doing that, let's look at the next quantum number, m sub L, the magnetic quantum number. The possible values of the magnetic quantum number depend on L. They depend on the subshell. So in this case, m sub L, the smallest value is negative, and it turns out it's negative L. The largest value is positive, and it turns out to be positive L. So this is the minimum, this is the maximum, and in between are any whole numbers. So, for example, if L is equal to 3, m sub L starts at negative 3, negative L, and it goes up to a maximum of positive 3, positive L, and therefore in between, 1 up from negative 3 is negative 2, negative 1, 0, positive 1, positive 2, and positive 3. So we get 1, 2, 3, 4, 5, 6, 7 values. And what does this tell us? Well, if you look in the textbook, it says that it determines the orientation of the orbital. Essentially, what directions the orbital can point in. I'd like to tack on one more thing to this and go ahead and say that in addition to telling us the orientation, the directions of orbitals, the number of values of m sub L indicate how many orbitals are in that particular subshell. So if we go back to our previous example, in the L equals 3 subshell, and this is often called F, that's the one-letter name, there are 1, 2, 3, 4, 5, 6, 7 values. There are 7 F orbitals. And we'll see another example of that in a minute. Finally, the last quantum number, which will be a lot easier than the previous ones, are the spin quantum number. The possible values are +1/2 and -1/2. This is often referred to as spin up and spin down, and later we'll show it as an arrow up or an arrow down. And essentially, they're not really spinning around, but if you put a magnetic field near these electrons, if the magnetic field is pointing up, the electrons will all either go up with the field or down opposite the field. They'll be forced to do this, and this magnetic property we call spin. And in terms of what it tells us, because there are 2 possible values here, that means 2 electrons can fit in each orbital. Later on, when we start Chapter 8, we'll look at how these quantum numbers help shape the periodic table and will help us determine reactivity of atoms.